Let's compute the expected value and the variance of beta distribution with parameters alpha and beta. So we have some random variable x with parameters alpha and beta. We have the PDF of x, which is given by x to the alpha minus 1 times 1 minus x to the beta minus 1, divided by the beta function of alpha and beta, and multiplied by the indicator function that x is from 0 to 1. So this indicator gives us that the PDF is equal to this expression only if x is from 0 to 1. Otherwise, the PDF is going to be equal to 1, right? And then here we have the beta function. So the beta function is given first by the integral from 0 to 1 of t to the power alpha minus 1, 1 minus t to the power beta minus 1 dt. Okay, so this is the definition that we have for the beta function. But we can also express the beta function as a function of the gamma function. So the beta function is given by the of alpha and beta is given by the gamma function of alpha times the gamma function of beta over the gamma function of alpha plus beta. Okay, so we will have to use this definition and this one for computing the expected value and the variance. Okay, so we want to compute first the expected value. To compute the expected value, we just have to use the formula that we know for so since we have that x is an absolutely continuous random variable, then we have to compute the expected value as the integral of x multiplied by the PDF, right? So we will have that the expected value of x will be given by the integral from minus infinity to plus infinity of x multiplied by the PDF. And that's it, right? So now first I just have to replace the PDF by the PDF that I have right here. So let's do it. We have the integral from minus infinity to plus infinity of x by the PDF. The PDF is equal to this, so x to the alpha minus 1, 1 minus x to the beta minus 1, divided by the beta function of alpha and beta, and the indicator random variable, sorry, the indicator function, just the indicator function that x is from 0 to 1, dx. So the first thing that we have to do is that since we have an indicator here that x is from 0 to 1, then it means that the integral itself is going to be 0 if x is not from 0 to 1, right? So I can just change the limits of the integral right here. So I will not have the integral from minus infinity to plus infinity. I will have the integral from 0 to 1. And then I don't have to write this indicator anymore. I can just keep the x. And then I just have to compute this integral, okay? So look, here we have the beta function of alpha and beta. The beta function is a constant, so this is a number. So for any given alpha and beta, real numbers, positive real numbers here, the beta function is some specific expression, right? So this is a constant that doesn't depend on x, so I can write this constant outside the integral. So this will be equal to 1 divided by the beta function of alpha and beta. And then I will have the integral from 0 to 1 of x to the power 1 plus alpha minus 1. So here we have x to the power alpha, okay? But let me write this in the following way. Let me write it x to the power alpha plus 1 minus 1. Okay, so this is just alpha. This is just alpha, but I want to write it this way for some specific reason that you will understand in 2 seconds, okay? Then we have to multiply by 1 minus x to the power beta minus 1. And finally, we have dx. Okay, so first we have to notice the following. We have to notice that this integral is exactly the same to this one right here, with one little difference that instead of alpha that we have here, we have alpha plus 1, but the other things are exactly the same, right? So actually, this integral from here is just the beta function of alpha plus 1 and beta. So this integral is equal to the beta function of alpha plus 1 and beta. Okay, now we can just replace the beta function by the expression using the gamma function, and we can find the answer. So we will have that this is equal to the following. So 1 divided by the beta function of alpha and beta will be the gamma function of alpha times the gamma function of beta. divided by the gamma function of alpha plus beta. And then we have the gamma function of alpha plus 1 times the gamma function of beta divided by the gamma function of alpha plus beta plus 1. Now we just have to use the properties that we have for the gamma function. We know the following. So let me write that property over here. We know that the gamma function of alpha plus 1 equals alpha times the gamma function of alpha. Okay, so this is very easy to see if we remember that the gamma function is just, so if alpha is an integer, so we know that if the gamma function of alpha plus 1, let me write it, will be equal to alpha factorial if alpha is a positive integer, right? So it's clear that since here we'll have alpha factorial, then here we'll have alpha times alpha minus 1 factorial. So this property is clear if we do remember the definition of the gamma function for alpha being a positive integer. Okay, so we can use this property, okay, but again, this property holds for any alpha, right? It doesn't have to be an integer. But when alpha is an integer, it's very clear where we're getting this from. So we can see the following. We can see that we can cancel this. Well, first we cancel the gamma function of beta by the gamma function of beta. And then here we'll cancel this with this. Here, so this is equal to the gamma, so alpha times the gamma function of alpha. So from here we'll keep alpha. And from here we'll cancel this with this. Here we had alpha plus beta times the gamma function of alpha plus beta. So here we'll have just alpha plus beta. And this is the expected value of x. So alpha divided by alpha plus beta. So for the variance, we have the following formula. We know that the variance of x of any random variable is given by the expected value of x squared minus the expected value of x, and the whole thing is squared. Okay? So from here, we already computed the expected value of x. We already know that this is equal to alpha divided by alpha plus beta. And now all that we need to find is the second moment of x, so the expected value of x squared. Okay? So the formula to compute this is very similar to the formula of the expected value. The only difference is that instead of x, we'll have x squared, because here we have a function of the random variable x, which is equal to x squared. So here I need to write x squared, but here I need to keep exactly the same PDF that I had before. So just the PDF of x, okay? So we'll have that the expected value of x squared is given by the integral from minus infinity to plus infinity of x squared by the PDF of this random variable. Now let me replace that. But before replacing, let me notice again that here we have this indicator. So we can, from the very beginning, we can see that here the integral is not going to be from minus infinity to plus infinity, but it's going to be from 0 to 1. So we'll have the integral from 0 to 1 of x squared by the PDF, so x to the alpha minus 1, y minus x to the beta minus 1, divided by the beta function of alpha and beta, and dx. Okay, now look, so the steps that we have to do right now are very similar to the steps that we did before for computing the expected value. The only difference is that here I have a square. So here I will have x to the alpha plus 1. Okay, so look, so first let's take this constant outside. So we'll have that this is 1 divided by the beta function of alpha and beta. We already know that this is equal to this. So let me write this from the very beginning. So we have the gamma function of alpha plus beta divided by the gamma function of alpha times the gamma function of beta. And then I'm going to multiply this. So we'll have here the integral from 0 to 1. And here I will have again x to the power alpha plus 1. Let me write it in the following way. X to the power alpha plus 2 minus 1. Okay? So this is x to the power alpha plus 1, right? And then we have times y minus x to the power beta minus 1 and dx. So following exactly the same logic that we had before right here, we can see that this is just the beta function of alpha plus 2, so this is just the beta function of alpha plus 2 and beta. So let me again replace this using the gamma functions. Then we obtain the following. So first of all, we have this part. So we have the gamma function of alpha plus beta divided by the gamma function of alpha times the gamma function of beta. And then we have the gamma function of alpha plus 2 times the gamma function of beta divided by the gamma function of alpha plus beta plus 2. And now we just have to cancel whatever we can cancel here using this property. And we will have the answer. So we'll have that this is equal to the following. So this is equal to, so what can we cancel here? First, we can cancel the gamma function of beta, okay? Then this, we can cancel this gamma function of alpha with this, but then we'll have that this is equal to alpha plus 1 times alpha. This is alpha plus 1 times alpha. Okay, so this is what we get when we cancel these two gamma functions. And finally, we can cancel this one with this one. So in the denominator, we'll have alpha plus beta plus 1. And then we'll have alpha plus beta. So this right here is the second moment of the random variable x. So all that we have to do right now is to replace this into the second moment and the expected value into this so we can find the variance. So let's do it. So the variance of x will be given by this alpha plus 1 times alpha divided by alpha plus beta times alpha plus beta plus 1. And we'll have minus the expected value squared, so alpha divided by alpha plus beta squared. And we can write this in the following way. So this is usually how you will find it in books. So here we'll have alpha times beta divided by alpha plus beta squared times alpha plus beta plus 1. And this right here is the variance of the random variable x.